Okay, all right. So, let us begin the next lecture. The last thing we saw in the previous class was about minimum distance, but I want to recap what we saw in the previous lectures. Let us do a quick recap. Okay, so right now we are thinking of 3 parameters for any code, nkd code. Okay, so once again clearly this is going to be a k dimensional subspace of f2n, there is no change in that. But what is this new parameter d now? D is minimum over u not equal to 0, u in the code, the Hamming weight of u. Okay. So, you look at all the non-zero vectors in your code, the one that has smallest, you pick the smallest Hamming weight among all those things, you get the minimum weight. Okay. So, that is what we saw, and then this minimum distance d, like I pointed out, it is not a very linear algebraic parameter, it is more of a combinatorial parameter. Okay, so, it is more difficult to determine directly. The only relation it has with the parity check matrix is the following relationship. You can also show d is the what? It is the minimum number of columns of H that add to 0. Okay, well, the 0 vector. Okay, so I guess it is clear. So, if I say the nkd code C has generator matrix G and parity check matrix H, okay, remember G is a k cross n matrix, full rank, and H is a n minus k cross n matrix. Okay, you can think of them in systematic form. If G becomes IP, H will be P transpose I. Okay, and then the relationship GH transpose equals 0 is also satisfied. Okay. So, these are all the things that we saw in the last class. Like I pointed out, this is hard to determine in general. Okay. So, usually the strategy is to design a parity check matrix H and then show some d minus 1, when any d minus 1 or fewer columns are linearly independent. If you do that, then your minimum distance is at least d. Okay, so that is the strategy that is used to show. So, if you want to show it is exactly equal to d, you also have to find a set of d columns which do definitely add up to 0. Okay, so, you do that, you can find these things. Okay, so let us see a couple of quick examples. I am going to throw out a couple of parity check matrices at you and then ask you for the minimum distance. We also started on the Hamming code, I think. Okay, so we will come back to that soon enough, but before that let us just quickly see 2 quick examples just to drive home this point of how easy it might be to find the minimum distance. Okay, so here is the first example. So, okay, so try that. The next example you might want to try. Okay. So, let us see the first example. I have a parity check matrix. Okay, the easiest thing to determine is what? What is the first easiest thing to determine? N is the easiest parameter that you can determine. Okay. Now for n minus k, so okay 6, I am sorry, see even the easiest parameter can sometimes be hard. Okay. So n equals 6, and then the next thing that you can determine is from the parity check matrix the number of linearly independent rows, and that would be n minus k. In this case n minus k is what? Okay, so in this case the form of the matrix is easy enough that you can quickly see that the 3 rows are linearly independent. Okay, so you have an I sitting inside it, so from there you can quickly see that n minus k is 3. So from there you can quickly conclude that k has to be 3s also. Okay, what about minimum distance? Okay, so it's very safe when you compute minimum distance to be patient and eliminate one after the other and then go to 3. Okay, so don't quickly jump to 3. I mean, in this case it is 3, the answer is correct, but it's good to do it step by step. The first step is, first of all, it's not d equals 0, you know d is not 0, that you know. What about d equals 1? How do you eliminate d equals 1? Okay. D equals 1 can happen only if there is a all 0 column. Okay, there is no all 0 column, so d equals 1 is eliminated. Okay, it cannot, d cannot be 1, it has to be at least 2. Okay, now for 2 what should happen? 2 columns should be identical, should repeat, and you can see there is no repetition here, so 2 is also not possible. So d has to be at least 3, and can you find 3 columns that add to 0 is the question. Okay. Yeah, so there are multiple choices possible. Okay, so for instance if I pick this column and this column, they add to 0. Okay, so d clearly becomes 3. Okay, so now another question that might be of interest is how many minimum weight code words are there? Okay, that might be an interesting question to think about. Okay, so these are again difficult questions, but you can try to answer that. For instance, in this code, how many can you quickly see? Okay, so the one that I put down is clearly a minimum weight code word. Another one that you can have is this one and this one, right? So another one you can have is this guy and this guy. Anything else? Is anything else possible? Yeah, so notice there is like a non-trivial looking minimum weight code word. Okay, so those 3 things if you add, you get what? 0, right? Yes or no? Okay, so that's 4. Okay, can there be anything more? So in this case it's a really simple problem, there are only 8 code words, right? So you can enumerate everything and find the answer very easily. So I believe these are the only 4 code words which are of minimum weight in this. Okay, so you can also find the other ones. These are the, am I right? Correct? Yes? Everybody is happy? Okay. So there are 4 of them. Okay, so it can be a bit more devious, right? So that's the only thing I want to point out. There can be some hidden code words which suddenly will show up. Okay. All right. So let's now move on to the other case. What about the other one? Okay. So once again you have to follow the same strategy. Okay. So you have to start with d equals 1. Well, d equals 0 you can just throw away just based on what you know. Okay. So if you want n and k, let's say n is 8 and then n minus k is 4. Okay, so these 2 things we are able to see quite easily. N minus k 4 is easily seen because once again there is an I sitting there. If you do not have an I, you have to do the Gaussian elimination, generate the I, and then you will see that it works out. Okay. For d you have to do a little bit more work than before. Okay, let us see, d equals 1 is definitely ruled out. What about d equals 2? That also is ruled out. What about d equals 3? Everybody is sure? Definitely sure? You have to really, yeah. Okay, you have to check. Okay, even within these, what did I do? Okay, so even within these guys, you have to check that no 3 adds to 0, and then maybe 2 of them will add suddenly, and they'll give you something which is weight 1. You know, I mean, it can happen. So if I make one, here in this case it won't happen, but if I make one devious looking change, it can suddenly happen. For instance, if I just remove this 0 and make it a 1, what can happen? Okay, so you see the last 3 adds up to 0. So it's a little bit more non-trivial to find minimum distance, but in this case you can show no 3 columns will add to 0. Okay, so I am not saying it is easy to check that, but you have to check all possibilities. How many possibilities you have to check if you were to do an exhaustive search? 8 choose 3, but clearly you do not have to do all 8 choose 3, right? What can I avoid easily? Among the first 4 columns, there is no way anything is going to add up to 0. Okay, so there is no problem there. So you can completely remove that under consideration. You cannot completely remove, but you can take, you can don't have to take everything from there. So you can reduce it if you like, you can be smart about it, but at the end of the day it is some kind of exhaustive checking. There is nothing much you can do. Okay, so D will not be 3. What about 4? Okay, so 1 2 3 4, not 1 2 3 4. Okay, so there are multiple possibilities. Okay, so multiple possibilities to get that. For instance, very interesting looking example you can come up with if you like. Yeah, so if you take this guy and this guy, what happens? That would be a code word, right? Just to give you a non-trivial example. So some strange things like this can happen. So you can get D equals 4. Okay. So this is the procedure. Think about it very hard. I mean, I remember the first time this was taught to me, I thought about a lot of, I mean, algebra type of algorithms that should give me the minimum distance. You know, I mean, after all, I can put it in IP, and there is only an I, there is a P, and very well smarter people than me have thought about it. But anyway, the final computation as you have to do always will end up being an exhaustive computation. It is very difficult to do a smart algorithm, like it is NP complete, and I do not know if you are aware of a very recent work that is out there saying P may be not NP, so maybe nobody will have an algorithm. Okay, so it's a difficult problem. Okay, any questions? Yes. Yeah. Yes, of course. I mean, as you go larger and larger, then 8 choose 3 kind of, n choose 3 will become better than 2 per k. If you're doing more. Yeah. In this case, there are so many other ways of doing it. So, anything else? It's okay. All right. So let's move on. Let me come back to this Hamming code. Okay. So the code that we saw. Okay. So I think the idea was to construct a parity check matrices with D equals 3, right? That was the idea, and we are going to pick R rows. Okay, and okay, so this is the parity check matrix that we are going to construct, and one of the choices for n is to pick n equals 2 to the power r minus 1. Okay, and then here you put all non-zero binary R tuples. Binary R tuples as columns, okay, not as rows. Okay, this is going to go into columns, and you get a parity check matrix, and clearly D will be 3 for this. Okay. What will be n minus k? Will be equal to R. Okay, so both these things need proof. Okay, proof is not too difficult. Okay, why will n minus k be equal to R? You can find a IR inside this matrix. Okay, so you will have all those guys, and that will give you a linear, give you the linear independence that you need. Okay, so you will get n minus k equal to R. Okay, and then D equals 3 you can easily see. Okay, you add two things, you will get another R tuple which is also non-zero presumably, and then you also have it somewhere occurring. So you will get D equals 3. Okay, so what are the general parameters of this code? N is 2 power R minus 1, and what is k? So 2 power R minus 1, and what is D? Okay, so these are general binary Hamming codes. Okay, binary Hamming codes. Okay, and R can be, if you want, you can start with 1 if you like, but most non-trivial computation starts with 2. So let me just put R equals 1, 2, 3, etc. Okay, 1 I think doesn't make sense, so let's start with 2. Sorry. Okay, R will make k minus 1. R equal to 1 I think will make k equals 0 and all that. It just doesn't make any sense. So let's start with R equals 2, 3, etc. all right. So, these are the binary Hamming codes, and any d equals 3 code you might build with binary, any binary d equals 3 code you might build will look roughly like this, okay, and you have to make, if you want to make it very efficient, it will look like this, right. So, you know how d equals 3 can be satisfied, there should be no repetitions, there should be no all 0 column, okay, that is it, and you get d equals 3, seems like a very simple recipe and it is not too hard, okay. So, many codes will have d equals 3, all right. So, that is the Hamming code, we have already seen some, we have already seen this code before, but I think it is good to see it once again. Okay. So, d equals 4 onwards becomes a little bit more interesting. So, d equals 4 is not too hard, it turns out you can get a d equals 4 code from a d equals 3 code, okay, and that is close to optimal, you can't do much better than that, okay. So, we will see that next. So, what we are going to see next is some simple modifications of codes. Okay, so, we will see 3 ideas. The first idea I will call shortening, the next idea is puncturing, the third idea is extending. Okay. So, I have multiple purposes in discussing these modifications of codes. The first purpose is it will give you a feel for what these generator matrices are, parity check matrices are, how do you manipulate them, how the minimum distance gets affected and all that. Okay. So, when you discuss this, all that will become a little bit more clear and it is a good reinforcement of those ideas. And the other purpose is these things are extremely valuable in practice. Okay. So, maybe not extending, but shortening and puncturing are pretty much used in all practical applications. Nobody will just use a code, it will always be a shortened version or a punctured version. So, it turns out in practice to adjust some parameters, this is very crucial. So, from both points of view it is useful. So, we will see that. Okay. It is very simple ideas, but nevertheless important to see them in some detail. Okay. So, let us start with shortening. Okay. So, let us say we have an NKD code. Okay. So, C is an NKD code with generator matrix G. Okay, I am dropping this generator matrix all the time, maybe it is not a very good idea, but remember that when I say generator I mean generator matrix. Okay. Suppose you have C, code C given like this. Okay. So, we know how to write this set of all C such that C equals mg and m comes from the set of all binary k tuples, right. Okay. So, it is good to think of G as in a systematic form, at least for shortening you always think of G in systematic form IP. Okay. So, then the C becomes M and MP. Okay. So, what you do for the shortened version is, suppose, so I am going to now define the shortened version. We will call it C sub s, and this s is a positive integer. Okay. So, s is basically 1, 2, 3 so on. So, C sub s is basically, so let me write it down carefully. Set of all C, so let me just write it down a little bit differently. So, let me write the other thing first. Okay. So, the basic idea is to restrict your messages to have only k minus s non-zero possibilities. Okay. The last s bits of the message you will always set to 0. So, that is the idea behind shortening. Okay. So, you basically set, okay, what does this s tell you? set last s bits of m to 0. Basically you shorten your message, okay, more than shortening the code. When you shorten the code, you are shortening your message, okay. So you have the first k minus s bits as any bits that you want, and then the last s bits you force them to 0. So what will happen when I do that? When I do m times g,
the last 3 rows,
the last s rows of g will pretty much drop out of consideration. I only have to worry about the first k minus s rows. So when I form the code word, what will happen? The message part of the code word will have the first k minus s bits, okay, but then the last s bits of the message will always be 0, and there is no point in transmitting that, okay. I do not have to transmit that, okay. So I can just simply drop those s bits in the code also, the code word also, okay. So the way you write it is, okay, so you take it's always a little bit confusing to write it in a very optimal way, so let me just see. Maybe there is a efficient way in which I have written it here, let me see. Okay, so this seems like the best way I can write it. So you write it as m1, m2, so on till mk minus s, okay. So you take k minus s bits, and then what do you do? Leave out the 0. So the remaining things I am going to drop out, it just does not mean much, so I am just changing the generator matrix a little bit, and then what do you do? Okay, so it's a little bit more confusing, so let me just write it, and then we will worry about what happens, okay. So maybe I make it mp such that m is what? m1, m2, mk minus s, and then zeros. Okay, it's just a laborious way of writing, but I think it's good to write it once and see how it looks like, okay. Is that clear? So I can define another p prime if you want, which is just the first k minus s rows of p, and simply write it as mp, where m is simply the only the k minus s bits. You can do it that way also, it's just another way of writing, does not change anything, okay. Is that clear? Reasonably clear. So you basically restrict yourself to only the k minus s bits of the message, and the remaining bits you set to 0. Is there a question?
It's basically like having another code with k as being decreased by s. So what utility comes from?
Yeah, I'll come to that. So practical utility is valuable. Let's come to that slowly. Okay, the question was about practical. Why will it be useful? Yeah, I mean, see, you don't have to think of shortening as a great idea, but it's nevertheless a simple idea. Okay. So let's see. So the interesting question now is, what are the parameters for CS? Okay, what is the generator matrix for CS? What is the parity check matrix for CS? Those are the things that are interesting. Okay, so that's the thing I want to concentrate on a little bit. Like I said, it gives you practice with thinking about what these matrices are clearly. Okay, so let's start with the generator matrix for C. You have IK, and then you have. Okay, so let me write down the IK a bit more laboriously. 1 1 1, so on 1, you have zeros here, and then you have P, right? So P would be here. Okay, so this is the generator matrix for C. What would be a generator matrix for CS? Okay, maybe it is GS. The last S rows are 0. Is that enough? Okay, the last S rows are 0. That's fine. I agree with you. So it goes from 1 to k minus s, and from there below I just remove. Okay, I remove that. Then what else should I remove? Yeah, the last S columns of I also I should remove. No, that's the idea. This also should go away. It's quite simple to see, but anyway. Okay, the last s columns of I should also be dropped. Okay, so you would get a GS. Is that okay? So CS would be I k minus s, and then you would have P from 1 to k minus s. Okay, so you do not include the. Is that okay? All right. So what about parameters? Okay, so here you had nkd. What will be the new parameters now? As usual, n is the easiest. N will become n minus s. What will k be? K minus s. Okay, you are able to see that immediately, right? You have an I k minus s here. What about d? What about d? So it cannot go down. Okay, so that's the most important thing. Okay, when you shorten, d will not go down. So you will get greater than or equal to d. How do you quickly show that? How do you show that d cannot go down?
More than weight of code words in CS, because in CS you are assured that the last S bits are 0.
You used to giving intuitive engineering answers. Okay, if you have to write a precise proof, you have to write it in terms of contradiction. Okay, so you have to assume now, suppose CS has a code word of weight, say some d prime which is strictly less than d, then what will happen? Suppose CS has a C belongs to CS and CS, it is non-zero, C is non-zero and weight of C is equal to some d prime which is strictly less than d. Then what can I do? I can now create a C prime which will be what? C1 so on till C k minus s, and then what will I do? I will add zeros, and then what will I put for the remaining guys? C k minus s plus 1 all the way to C n minus s. Now what should C prime be? Should C prime be anything special now? Should it belong to any code that you know of? Maybe any code that is in this page? It should belong to C. Okay, so this implies C prime belongs to C. Why? I got C by shortening a code from the code word from the original code, right? So if I go from a code word in the shortened version, add zeros at one point, I should get a code word in the original code. And now what can happen to weight of C prime? That is going to be d prime, which contradicts the assumption on the minimum distance of C. Okay, so that implies minimum distance of C. Okay, let me write it down carefully. Minimum distance of C is less than d, which is a contradiction. And so our basic assumption cannot be true. You cannot find a non-zero code word in CS which has weight less than d. Okay, so simple enough proof, but if you have to write it down, you have to be precise about it. Okay, so this is how it works. So in most cases, when you shorten, it will be equal to d. Okay, so unless you are really lucky or you shorten with a lot of foresight, you cannot get a big jump in minimum distance. But sometimes it might happen that you get a larger minimum distance. Okay. Okay. So the question was, what is the point in doing this? It looks like you are not gaining anything, you are just designing another linear code with different parameters n minus s, k minus s. Okay. So it turns out the way we do our design, if you want a particular minimum distance d, you can design it only for certain special values of n and k. Not all possible n and k is possible from the design point of view. You may not be able to design nkd codes. You will see some design strategies later on in the course. You will see that those strategies work only for certain specific values of n and k, right? Maybe that's how it works. And then you might want some other n and k which is very close to the n and k. I mean, maybe you want n minus s, k minus s. Right? So then how do you do it? You do it by shortening. Okay. So that's how it is used in practice. So you design a larger code and then you shorten it to get what you want. Okay, so that's how it's used all the time. Okay. All right. So what about the parity check matrix? This is a more interesting question. Okay, suppose I have a code C which has a parity check matrix which looks like this. Okay, let us say P transpose and then I n minus k, right. So this is for the original code. What will happen to the parity check matrix of the shortened code? Okay, first of all let us take a small minor step first. What will be the dimensions of the parity check matrix of the shortened code? N minus k cross n minus s. So clearly what does this suggest? Nothing in the rows will go away. Okay, so you do not have to keep removing anything from the row, only the columns have to go. So which columns will have to go?
S columns of P transpose.
Okay, the last S columns of P transpose have to go. Okay, so that is the idea. Okay, so you will just look at the last S columns of P transpose and it will go. Okay, remove the last S columns, you will get this guy here. Is that okay? So if you are not able to quickly see it, I will suggest another way of thinking about the parity check matrix. So far for the encoder, we have always been using the generator matrix. You can also use the parity check matrix for encoding. Okay, so nothing stops you from doing that. See, you have H equals, let us say P transpose I. Okay, the columns of the parity check matrix are associated with the bits of the code word. See, remember what is the condition? You want H times C transpose to be 0. So if you have Ck here, Ck plus 1 all the way to Cn, this has to be equal to 0, right. So I can associate each of these bits with the columns of the parity check matrix. Okay, if I have a valid code word, what should happen? These columns will be multiplied by those bits on top and I have to add them up, I should get 0. Okay, remember this is my message part. Okay, so once I fill in my message part, how will I compute my parity part? The equation directly gives you the answer. All you have to do is simply multiply the columns by those bits, add them up, whatever vector you end up with will simply become your parity, right. That is what this equation is, right. So I can write this equation as Ck plus 1 through Cn as simply being equal to what? Okay, so I have to write it carefully, P transpose times C1 through Ck. Okay, so that is exactly what this equation means, written in a different way. Okay, so I can load my message bits on top of P transpose, multiply the columns, add it all up, I will get a vector at the end, n minus k length vector, and that vector is exactly my parity vector. I have to just rotate it and send it out. Okay, that is what this equation means. Now in shortening, what am I doing? My last S message bits are 0, which means the last S columns in P transpose simply drop out. You do not have to worry about them. Okay. So this way of viewing the parity check matrix is also useful. Okay. So now once again, once you think in terms of parity check matrix, even the minimum distance becomes a little bit easier to argue. Okay, from previously I had to write down some contradiction proof and all that, but from the parity check matrix it is just immediately clear. Okay, if you had d columns of Hs adding to 0, what will happen? Same d columns in H will also add to 0. So clearly there will be a problem. So that is another way of thinking about it. It is the same argument, but maybe when you stare at it, this is an easier thing to get to the answer. Okay. All right, so let us move on to the next part of it, which is puncturing. Okay, so I finished shortening, we will see puncturing. Okay. So puncturing is a little bit easier to describe. Okay. So puncturing is basically the idea is to drop parities. Okay. And this is a very powerful idea, it is used a lot in practice. Okay. So you drop parities. So let me just describe what happens. So once again, suppose C is an NKD code. Again generator would be G, etc. Parity check matrix H. Okay. So the punctured version, you need once again an integer P, which would be 1, 2, 3, so on. Cp basically B. Okay, so I am going to think of everything in systematic form. So G is going to be IP, and in my code the last n minus k bits will be parity and the first k bits will be message. Okay, so when I drop parities, all that I do is it is going to be C1, C2, so on till Cn minus p, such that C1, C2, so on till Cn minus p, Cn minus p plus 1, so on till Cn, such that belongs to C. Okay. So this is the punctured version. Okay, so you take all the code words of C, simply drop the last p parity bits. You will have the same number of code words left. How do you know that no repetition will happen? Yeah, so I have to pick p carefully, right? So I cannot go beyond n minus k. Okay, so I won't go beyond n minus k. So I will make sure that the first k bits are not affected by the puncturing. Okay. So definitely I won't lose code words if I do this, because the first k bits are message bits and I am not puncturing any of that. So they will all be distinct in my 2 per k code words. So as long as I drop parities, my number of code words will not go down. Okay, I will have the same number of code words, everything will work out. Okay. So let us quickly see what will happen to the generator matrix. Okay, if you have IK P, what will happen to GS? GP, I am sorry, yeah. So you will have the same IK, right, nothing changes there. What will happen to P? The last P columns will simply drop out. Okay, and you get whatever you had. Okay, puncturing is very easy to describe. What about NKD, the 3 parameters for the punctured version? Okay, so this is going to be n minus p, k remains k. I just showed you why k remains k, no problem. Yeah, so this is going to happen, k less than or equal to d. Okay, but I mean, it is not good to just say less than or equal to. So then it looks like I am suggesting it can go to 0. Can I put a greater than or equal to? Let me put a greater than or equal to. Also, you can also say n minus p k greater than or equal to what? Can I say it will be greater than or equal to what? Cn minus k. Oh my god. Very simple. D has to be involved in the answer. Okay, so what will it be greater than or equal to? Simple formula. Can I say d minus p? Yeah. D minus p is okay, no? What's wrong with d minus p? That is a perfectly good enough expression. Why is d minus p okay? So the intuitive argument is in the punctured, in the original code, right, there will be there will be some code word with minimum weight d, okay, minimum weight d. When that gets punctured, p bits are dropped. The worst case that can happen to you is all p got punctured, all p were 1 in the last p bits, and in that case it will be d minus p. In any other case you are not at an advantage, so you can only, it cannot be worse than this, greater than or equal to d minus p. Okay. So I will leave it as an exercise to see what happens to the parity check matrix in puncturing. Okay, it will be a little bit more complicated. It will be like what happened to the generator matrix. Okay, so you will see when you in the generator matrix for shortening. Okay, what happened in the generator matrix for shortening was a little bit more complicated, right? Nothing just get dropped. Same thing will happen here in puncturing in the parity check matrix. It will be a little bit more confusing. Okay, but I want to quickly point out one thing. So what does shortening do to the rate of the code? Okay, what do shortening and puncturing do to the rate of the code? Okay, so you had an NKD code. Okay, suppose you do two things. You go to CS, which is shortened by S bits, or you go to CP, which is punctured by P bits. Okay, so what you get here is n minus S, k minus S, greater than or equal to D. What you get here is n minus p, k, and then let us say greater than or equal to d minus p. I will say that on a positive note. Okay. So what happens to the rate here? Okay, the rate here is k by n. The rate here becomes k minus s by n minus s. For s equals 1, 2, 3 and all, how will this compare with k by n? It will be smaller. Okay, it will be smaller than k by n. You can show that, it is very easy, just cross multiply, see some nk will cancel and see yes, it will work out. If n is greater than k, this will always be lesser. Okay, so this is the condition. So when you shorten, the rate goes down and the minimum distance can possibly increase. Okay, when you puncture, what happens to the rate? Rate goes up. Okay, k by n minus p is greater than k by n, but the minimum distance can possibly come down. Okay, so this is what will happen. Okay. So puncturing is always used. For instance, in any standard communication standard that you pick up, there will be puncturing. Okay, they will always design a code with lower rate and puncture it to get higher rates. What could be the advantage of doing that? Instead of designing two different codes, one at some rate, say rate half, another at rate 1 by 3, you will see most standards will design only one code at rate 1 by 3 and will puncture to get a rate half code. Okay, that is a very standard numbers, is half, 1 by 3 and half are very, very standard, you will see in almost all standards. Why do they do that? Why don't they design two different codes for rate half and rate 1 by 3? Yeah, so it's about reducing complexity of encoders. Whenever you want to put these encoders in some devices which are, say, consume battery and you want to conserve battery, you might want to have some simple decoders as opposed to remembering a lot of things and all that. Okay, but nevertheless that is not too much of a problem because encoding is not terribly difficult, but it turns out decoding also might become easier. Okay, you can have just one decoder which runs for all of these codes. So those things are advantageous from a design point of view. Okay, if it is not so important, then you might want to design two different codes. In fact, if you design two different codes, you might be slightly better off, but you are not considerably worse off by doing puncturing and shortening. That is the idea. Okay, so the last thing, we have about 6 minutes, so let me do the last thing, which is extending. It is not too difficult, it is an easier thing. Okay, so once again you have C, which is an NKD code. Okay, generator G, parity check matrix H, and once again I am thinking of this as systematic form. Okay, so these are quite standard. Okay, when you extend, you do CE. Okay, E is not any integer or anything, it is just an extension, I am denoting it as CE. Okay, what this has is C1, C2, so on till Cn, and then here you have C1 XOR C2 XOR, okay, so on till, I am writing XOR because I want to drive home the point, it is just one bit for all C1, C2, Cn belonging to C. This is the idea. Okay, so extending is basically the act of adding an overall parity. that is the idea in extending. Okay. So, the way to visualize this is you have the list of all code words listed down one below the other. What do? You go to each code word, compute the overall parity and add an extra bit and put that as the parity. You do that, you will get this. Okay. So, that is the idea. So, the parameters, we will quickly write down the parameters. The original code is nkd, the parameters will be what? N plus 1 k, k remains k because you are adding only a parity, you are not adding any new message bit. Okay. So, it is going to be just parity added, so it is just k, and then what? D or d plus 1, when will it be d and when will it be d plus 1? Okay. So, depends on whether d is even or odd. If d is even, then what will happen? It will remain by itself. So, there is no point in extending a code with d even. Okay. So, that seems like a bad thing to do. So, one way to write it would be to say d plus d percentage 2 or d mod 2. Okay. So, if d is even, I get d again. If d is odd, my minimum distance goes up by 1. Okay. And the loss in rate is negligible, right? It is k by n plus 1, and if k and n are fairly large, just do not lose anything. For not losing much, you have increased the minimum distance by 1 to go from odd to even. Okay. So, this is extending. A very interesting exercise which I urge everybody to strongly try is get the generator and parity check matrix for the extended code. Okay. So, it is a little bit non-trivial, you have to do some work. Okay. It is not very non-trivial, but anyway it is a good thing to try. You will get a good idea of what these parity check matrices and generator matrices look like. Okay. Right. Everybody is quickly thinking about what happens. Okay. So, it is not too difficult. Think about it. Okay. So, that is an important exercise, I urge you to try it, you will get a clearer idea of what happens. Okay. So, we saw a few techniques now to see shortening, puncturing and extension. Basic idea, like I said, was to get you familiar with what the parity check matrix is, generator matrix is, what it means, how do you manipulate, etc. Hopefully, that is a little bit clear. But another point I want to make about this nkd is the following, which you can imagine, which is not too difficult, but still there are two conflicting notions here. One is k by n, which is rate. Okay. Okay. Another thing is basically minimum distance, but I will normalize it just to make sure I can compare it with the rate. Normalized minimum distance, which is d by n. Okay. So, these two will kind of compete with each other. Okay. I want to increase both, right, in some sense. Like I said, minimum distance is connected to the error correcting capability. If I have more minimum distance, I can correct more errors. Okay. So, I want to have more d by n. Why do I want to have more k by n? Yeah, it's well, you're giving very obvious answers, you know. Then I can send more information per second, okay, at some level. So, I can get that, okay. So, I want to get k by n up, but you can imagine there will be some bounds. You can't keep on increasing k by n for a fixed n, you can't keep on increasing k and d, eventually something will stop, you have to, there will be some relationship. Okay. So, there are some bounds relating these quantities, okay, which is what we will see in the next lecture. Okay. So, we will see how to relate these two things with some very simple ideas, but your intuition will mostly be true, I mean, when k by n goes up, d by n will go down, that is the idea. Okay. So, we will stop here for now, I will pick up from here in the next lecture.